This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions for the 2019 AP Calculus exam free response question BC6. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading in Kansas City. And I'll highlight the solutions presented in these guidelines, emphasizing the steps or the expressions necessary to earn each point. I'll present the solution to each problem in a little greater detail, with more explanation than given in the scoring guidelines. And even though this was not a calculator active question, I'll show you how to use technology to solve parts of this problem. And then I'll suggest some problem extensions. These are additional AP Calculus type questions that involve some of the concepts associated with this question. This free response question involves a function f with derivatives of all orders. A portion of the graph of f is given, along with the tangent line to the graph of f at x equals 0. And there's also a table given which lists selected derivatives of f at x equals 0. In Part A, we need to use the information given to write the third-degree Taylor polynomial for f about x equals 0. In Part B, we need to start by writing the first three non-zero terms of the Maclaurin series expansion for e to the x. And then we need to use this result and the result from Part A to write the second-degree Taylor polynomial for e to the x times f of x about x equals 0. In Part C, a new function h is defined in terms of a definite integral. We need to use the Taylor polynomial found in Part A to find an approximation for h of 1. And finally, in Part D, we need to use the alternating series error bound to show that the approximation found in Part C differs from h of 1 by at most 0.45. Part A was worth 2 points. The first point was for any two correct terms of the third-degree polynomial for f about x equals 0. So if any two terms in this expression, or this one with some simplification, are correct, then the student earns the first point. And the second point was for including the correct remaining terms. Part B was also worth 2 points. The first point was for the first three non-zero terms of the Maclaurin series expansion for e to the x. And the student could simply write these terms from memory. There was no justification necessary here. And the second point was for the second-degree Taylor polynomial for e to the x times f of x. So, to earn the second point, the student had to think about which terms to use in order for the product to produce a second-degree polynomial. Then carry out the multiplication, and finally collect the terms. Part C was worth 2 points. The first point was for finding n antiderivative, and the second point was for the correct answer, that is, the approximation. And remember, on the AP Calculus exam, final numerical answers do not need to be simplified. So this sum is acceptable as the final answer. Part D was worth 3 points. The first point was for using the fourth-degree term of the Maclaurin series for f. Now this point is earned here because we are using a fourth-degree term of the series for f. The second point was for using the first omitted term of the series for h of 1 in finding the error bound. So there must be evidence that we are evaluating the correct fifth-degree term of h. And finally, the third point was for explicitly indicating or connecting the error bound to 0.45. Let's take a closer look at the solutions, and where appropriate, the use of technology to answer these questions. In Part A, we need to remember the formula for a Taylor polynomial. And since we need the Taylor polynomial about x equals 0, I guess we're really finding a Maclaurin polynomial of degree 3 here. So we need f of 0, which is 3 by reading the value from the graph. And we need f prime of 0, which is the slope of the tangent line given on the graph. And we can read the slope as rise over run and find that f prime of 0 is equal to minus 2. And f double prime of 0 and f triple prime of 0 are given in the table. So here's the formula for the third-degree Taylor polynomial about x equals 0. Using the values from the graph in the table, I get this expression. And then a little simplification gives me this polynomial. Now, this may be overuse of technology, but here's a way I can use the TI-Nspire to produce this Taylor polynomial. This at least provides, I think, some good practice with notation and the general formula for a Taylor polynomial. So, using the TI-Nspire in a lists and spreadsheet page, I entered the values for the various derivatives of f in a list that I named f0. Then, on a calculator page, I used an appropriate formula to produce the third-degree Taylor polynomial. Here's an example for you to try. And this problem involves a Taylor polynomial, but this time, the derivatives of f are given via a formula. So, suppose f has derivatives of all order for all real numbers. If the nth derivative of f at 0 equals n plus 2 factorial, for n equals 0, 1, and 2, and on, find the fourth-degree Taylor polynomial for f about x equals 0. In Part B, the first thing we need is the first three non-zero terms of the Maclaurin series expansion for e to the x. Now, some of us might simply remember the Maclaurin series for e to the x. But otherwise, we need to find the nth derivative of e to the x and evaluate each of these derivatives at x equals 0. And the value is always 1. So here's the general formula for the second-degree Maclaurin series expansion for e to the x. Use the values of the derivatives. And then just a little simplification yields this polynomial. Next, we need to multiply the appropriate expressions for e to the x and f of x. And that means we need to account for all of the products that will produce a term of degree 2 or less. So, as I consider the possible products in the Taylor polynomial for f of x times the Taylor polynomial for e to the x, this expression will produce all the terms of degree 2 or less. So here I multiplied through, or distributed, and finally I collected the terms to produce a Taylor polynomial. Here is a way that I can use technology to find this final Taylor polynomial. So using the TI-Nspire, I first multiplied the two polynomials together, the one that approximates e to the x, and the other that approximates f of x, and I included all the terms given for each. Now the result here is a factored polynomial. In some sense it's simplified, but it's not in the form of a Taylor polynomial. So using the calculator command expand, I can now see all of the terms in the product, and simply read off the terms of degree 2 or less. Here's another example for you to try. Use some known Taylor polynomials to write the third-degree Taylor polynomial for each of these functions about x equals 0. You might try to check your answer using technology. On the TI-Nspire, try using the Taylor command. In Part C, we're given a new function h, which is defined in terms of a definite integral and the function f. And we need to use the Taylor polynomial for f from Part A to approximate h of 1. So, using the definition for h, I used the approximation for f as the integrand. And then I integrated term by term. And I evaluated. And this simplifies to 97 divided by 48. Here's a quick way to use technology to arrive at this answer. First, I defined the function h. And notice that I can define a function in terms of a definite integral on the TI-Nspire, and that's pretty cool. And then I simply evaluated this function at x equal 1. And I got the same answer, 97 over 48, thank goodness. In Part D, we know that the series for h converges to h of x for all real numbers x. And since the terms of the series for h of 1 alternate in sign and decrease in absolute value to 0, then the bound on the error for the approximation found in Part C is the next term in the series. Therefore, we need to consider this definite integral to produce the next term in the series for h of 1. So I found an antiderivative, evaluated, and simplified to 9 over 20. Therefore, the bound on the error is the absolute value of 9 over 20, which is exactly 0.45. Once I know the term needed as the integrand, it's pretty easy to use technology to find the value of the definite integral. To convert this to a decimal, I simply multiplied by 1 with a decimal point. And indeed, the bound on my error of approximation is 0.45. And finally, here are a few more problems for you to try. And these questions are related to alternating series. First, show that each series is convergent. And then, how many terms of the series are necessary in order to estimate the sum to the indicated accuracy? So these problems really deal with the error of approximation using an alternating series. I hope this video gives you a better idea of how to solve this free response question and how to use technology to solve and confirm your results. This problem presents some good opportunities to work with Taylor polynomials, alternating series, and error approximations. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.